Every time you fill up your car, you're tapping into the end result of a truly massive, kind of dangerous, and incredibly clever process. So today, we're going to pull back the curtain and go inside an oil refinery to look at the very first and maybe the most critical steps that turn that raw crude oil into the fuel that, well, powers just about everything. So picture this massive, complex facility. It's an absolute marvel of engineering. But the raw material it needs to survive, the stuff straight out of the ground, is actually its own worst enemy. What is hiding inside that crude oil that poses such a massive threat? Well, it's probably not what you're thinking. Yup, you heard that right. We're talking about hydrochloric acid. The same super corrosive stuff you'd find in a high-tech chemistry lab can literally be born right inside the pipes and towers of a refinery. This acid is the villain of our story today, and figuring out how to stop it is the key to the entire refining process. Okay, so to defeat our villain, we first have to understand where it comes from. And it all starts with what's already mixed in with the crude oil when it shows up at the refinery gate. See, the biggest problem isn't the oil itself, but what's tagging along for the ride. We're talking about brine, which is just super, super salty water, and it's full of these specific inorganic salts like magnesium chloride and calcium chloride. Plus, you've got a bunch of dirt and sediment floating around in there too. And here is where things get really bad. If you just take that contaminated crude and start heating it up, those salts have a nasty reaction with the water. Through a process called hydrolysis, the water basically rips the compounds apart, and in the process, it unleashes hydrochloric acid. That acid will just eat through steel pipes and towers from the inside out. It's an absolute catastrophic failure just waiting to happen. So how in the world do you protect a billion-dollar facility from destroying itself? Well, you build a really powerful first line of defense. The whole process is called desalting, and it's basically about giving the crude oil a really good wash before it gets a chance to cause any damage. The concept is actually pretty simple. It's like a two-punch combo. First, the oil gets a good mix to dissolve and pull all that salt out. We'll call that the mix. Then you've got to get that salty water back out of the oil. And for that, engineers use this really clever trick we're going to call the zap. All right, first up, the mix. The raw crude gets heated up to between 100 and 150 degrees Celsius. This is important because it makes the thick, goopy crude way less viscous so it flows more like water. Then it's blasted with fresh wash water and they're churned together. This creates an emulsion, think of shaking up salad dressing, and that gives the water a chance to find and dissolve all those nasty little salt crystals. And that brings us to the zap. This oily, watery mix flows into a huge vessel that has a high-voltage electrical grid inside. Now, oil doesn't conduct electricity, but the water does. So the electricity zaps the little water droplets, giving them a charge. This makes them instantly attract each other, and they start merging into bigger and bigger drops until they're so heavy they just fall right out of the oil and settle at the bottom, taking all those dangerous salts with them. But, it's never that easy, is it? Engineers are in this constant battle with something they call the rag layer. It's this thick, stubborn sludge of oil, water, and solids that builds up right where the oil and water meet. If this layer gets too thick, it can totally mess up the electric field and ruin the whole separation. It's a real headache to manage. All right, so with that nasty salt gone and the acid threat neutralized, our clean crude oil is finally ready for the main event. It's time to start breaking it down into all of its useful parts. The now clean crude gets pumped into a furnace and heated to a blistering 350 to 400 degrees Celsius. It's so hot that a huge portion of it instantly vaporizes. It flashes as it's sprayed into the bottom of this gigantic tower called the atmospheric distillation column. The best way to think of this tower is like a boiling point skyscraper. As all those hot vapors rise up inside, they start to cool down. Now, the lightest components, the ones with the lowest boiling points like LPG and naphtha, they travel all the way to the top floors before they cool enough to condense back into a liquid. Heavier things, like kerosene and diesel, they can't make it as high, so they condense on trays lower down. And the really heavy stuff, it doesn't even vaporize. It just pools at the bottom in the basement. So this leaves us with a really important question. That thick black gunk at the bottom, it's called atmospheric residue, it's still packed with valuable heavy oil molecules. But we can't just crank up the heat to boil it. Or can we? Yeah, that's a hard no. Heating it anymore would just destroy it. So engineers needed another elegant solution. And what they came up with is basically a bit of high school physics, just applied on a massive industrial scale. And here's why you can't just add more heat. Right around 400 degrees Celsius, those long, heavy hydrocarbon chains literally start to cook. The process is called thermal cracking or coking, and it basically just turns them into a useless solid carbon material. Think charcoal. It's a hard physical limit you just cannot cross. So if you can't turn up the temperature, what do? You change the rules of the game by lowering the pressure. We all know water boils at a lower temperature on top of a mountain, right? Where the air pressure's lower? Refineries do the exact same thing. They send that hot residue into a second tower and use a massive vacuum system to suck the pressure way down. And this really shows you the key difference. The first tower, the atmospheric one, works at normal pressure to skim off all the lighter fuels. But the second tower, the vacuum tower, operates at an incredibly low pressure. And that lets those valuable heavy oils, they're called vacuum gas oils or VGO, boil at a temperature below that 400-degree cracking point. It's such an elegant way to get around a hard physical limit.
So after all that mixing, zapping, heating, and separating under vacuum, what have we actually accomplished? Well, we've successfully taken this complex mess of crude oil and unraveled it into a whole series of distinct, valuable streams.
We now have all these separate products, and each one has its own journey ahead. We've got LPG, the lightest stuff. We've got naphtha, which is a key building block for gasoline, kerosene for jet fuel, and diesel, of course. The vacuum tower gave us that all-important VGO, which is prime feedstock for making more gasoline later. And the heaviest gunk left at the very bottom, that becomes stuff like asphalt for our roads. Going from a salty, corrosive raw material to a whole range of essential products, it's just an amazing journey of chemical engineering. And you have to remember, this is only the first step in the refinery. It really makes you wonder, what other hidden, brilliant processes are humming along just beneath the surface, powering our world every single day?